All right. Hello, everyone. Today's topic is digital signatures for blockchains. So I divided the talk almost into four parts. First, I will talk about discrete logarithm problem. Then we will talk about digital signature algorithm. Then we will move on to elliptic curves and talk about elliptic curve digital signature algorithm. Then I will give an example at the end showing that how a transaction in a Bitcoin works. So we will briefly see a basic transaction, transfer of Bitcoins to a hash of a public key. There we will see how the digital signatures work and how they are checked. So let's start with the discrete logarithm problem. Now that we know what a group is, we can define the problem as an element of group. So let capital G be a group and the small g its generator. Given A, it is feasible to compute G to the A. So I'm using the multiplicative notation here, but if it were addition notation, we will simply write A times G. Okay, so on one way it is easy to compute, but given B, which is actually G to the A, it is not computationally feasible to find A. So question is, it is easy to compute one way. When you know G and A, you can just compute the 8th power of G and find the element in the group. But conversely, if you know this element B and you know G, but you don't know A, I'm asking which power of a G provides this element in the group. And it is not that easy to do it. So we are saying that it is computationally infeasible. Okay, so here the important thing is that the hardness of this problem actually depends on the group. Okay, so generally we refer to this as interactability. So interactability of the discrete logarithm problem depends on the group. So this is actually the main point here, because this is why we are going to work on elliptic curves. Okay, so let's focus on this problem on many different groups. Let's consider rational numbers, and as a group operation we choose addition. So given B and G, now our problem turns into finding A such that A times G equals to B. Okay, so we know G, we know B, we are just wondering what is A. Okay, but if your group is just rational numbers and if your group operation is addition, now you can divide both sides with G. Okay, divide both sides by G, thus A becomes A equals to B over G. Okay, very easy to solve this logarithm problem here. So it is obvious that we cannot use this group for this kind of problems. Let's make it multiplication and let's move on to real numbers. Now the problem is the same. Given B and G, our aim is to find A such that G to the A equals to B. So when we do the addition, when we use the addition notation, this is how we define the problem. When we use the multiplication operation, this is how we define the problem. So we know B, we know G, and we are trying to find A. So most people confuse this discrete logarithm problem with this group, okay? So when you use real numbers, it is very easy to solve this problem, because if you take the logarithm of B to the base G, actually this becomes, A becomes log G, log to the base G of B. So by a simple logarithm operation, you can solve this problem and calculate the value of A. Okay, so this is not a discrete logarithm problem. This is the logarithm problem. So you might now understand why we're actually using the word logarithm here. Okay, it is very easy to solve it. So in order to hide our steps, make it a discrete problem, we are going to use finite groups. Okay, so let's move on to a finite group. Now let's consider ZP with respect to the operation of addition. So now the problem becomes, given B and G, find A such that A times G is congruent to B modulo P. Okay. Now the problem looks a little bit more complicated because we cannot solve it like a single calculation like we did it here. In the first example, since the one way of the operation was multiplication, we used division, which is the inverse of multiplication, and solve the problem. So in this case, one way is just taking the power of G. So it is an exponentiation operation, and the inverse of exponentiation is logarithm. So we solve the problem going backwards of that function, which is logarithm, and solve it. So in this case, we are again multiplying something, a times c, but now we have to do the division in modulo p, but division is not defined here, so we have to actually use inverse elements, right? So this problem again is easy to solve, because if we multiply b by G inverse, but this G inverse is inverse with respect to multiplication. If you multiply both sides with G inverse, what you obtain is that G inverse B congruent to G inverse times A times G, right? And this G and G inverse cancel each other. So G inverse times B becomes A modulo P. So I can solve this discrete logarithm problem if I multiply both sides with the inverse of G. And now the question becomes, is it easy to find the multiplicative inverse of an element, right? If it is easy, then I solve this problem in a very fast way. If it is hard, then maybe we can use this discrete logarithm problem with respect to this group. But in reality, it is easy to find G inverse because we can find multiplicative inverses easily simply by computing the extended Euclidean algorithm, okay? So again, the discrete logarithm problem is easy to solve here. So the main problem is that this discrete logarithm problem is not hard by itself. It depends on the group and group operation, okay? So as you can see on these three examples, of course, the first two examples were infinite groups, and we knew that it was easy to solve there. But as you can see here, it is also easy to solve. So we move on to groups where it will be harder. So let's move on to ZP, but this time the group operation is multiplication. So given B and G, find A such that G to the A is congruent to B modulo P. So now this is our problem. This is the discrete logarithm problem. Then the group is ZP and the group operation is multiplication. So far, the best known algorithms are sub-exponential with respect to the size of P, okay? So this is why actually we can use this discrete logarithm problem in practice. Okay, here's an example how it works. So I chose a prime number like this. So this is a prime number. So I calculated the x power of 3 and the result was this. So, you know, it is very easy to compute one way when you know the value of x because your calculations are in modulo this number. So it is actually modular multiplication, which is very fast to do it, but the inverse is not that fast. So if you do brute force attacks, you have to try every x value here and check if it gives this value. In reality, the answer is something like this. But of course, instead of brute force attacks, you can use some algorithms called index calculus type algorithms, which solves this problem faster than a brute force, because brute force attack will be exponential complexity, but we have sub-exponential time algorithms to solve it, okay? Now, so far we talk about the discrete logarithm problem. Now let's see how it works on elliptic curves. Instead of choosing groups like ZP or some other groups, now we choose the group generated by the points on an elliptic curve. So the elliptic curve discrete logarithm problem is defined as follows. Given an elliptic curve E defined over a finite field FQ, and you are given a point P on this elliptic curve of order n, and you have a point Q, which is actually d times P, which is actually adding P to itself d many times. So your actually elliptic curve discrete logarithm problem now here is that to find d. Your aim is to determine d. So you know P, you know Q. Now you are trying to find what is d, okay? So this is the elliptic curve discrete logarithm problem, and all of our security will depend on this problem, okay? And we will see why we are going to use elliptic curve discrete logarithm problem and not discrete logarithm problem in a minute, okay? So let's focus on discrete logarithm security. Polar draw algorithm can solve DLP in about P times Q over 2. It's in a square root. So This actually means that in, when we give the complexity in big O notations, we don't consider much about the constants here. So we can throw out pi and 2, and actually the complexity with respect to the big O notation is square root of q. So if q is 256-bit value, your time complexity is halved, which means 2 to the 128 operation. So polar row algorithm can solve this discrete logarithm problem with in O q of square root of q. Okay, but the thing is that index calculus algorithm can solve discrete logarithm problem on ZP, of course, with respect to multiplication with sub-exponential complexity. But here, this type of algorithms actually uses the fact that we are using small prime. We have, we can compare numbers in ZP because a number might be small, like 2 or 3, so we can use these properties. But when we choose the group as elliptic curve, there isn't small numbers or there isn't prime points or something. So index calculus algorithms uses relations between small primes, which is not applicable to elliptic curve digital discrete logarithm problem. So it is easier to solve DLP, but harder to solve elliptic curve DLP. That is the main point. Thus, using elliptic curves allows us to work on groups with smaller number of elements. So that is why we generally prefer elliptic curves over number groups. So let me give you an example and show you how the discrete logarithm problem is used in practice. So let's look at the Diffie-Hellman key exchange. The algorithm is simple. So Alice and Bob wants to communicate, and they haven't agreed on a key before, so they cannot communicate in an encrypted way, and the communication channel is insecure. So through this unsecure channel, they are trying to agree on a secret key. So algorithm works like this. Alice picks a random number A and sends G to the A to B. So G is the group generator here. B picks a random number B and sends G to the B to A. A computes 8 power of the number they receive from Bob. So it turns out to be G to the AB. And Bob does the same thing. So G to the A is received from Alice, and Bob actually randomly chose the number B. So he can also take the bit power of this number, and the result is the same. So throughout an unsecure channel, they agreed on a number which are now on the both sides. So this way they can use this information as a secret key if they prefer. So this number can be thousands of bits, and they may only require 128 bits. So they can simply choose, for instance, the leftmost 128 bits of this number. So let me show you this on a picture. So, and see why this is secure. So assume that there is a person, Eve, in the middle, who is a passive attacker. She only listens to communication and captures every communication. So the group generator G is known. And now let's assume that we are going to work on ZP. So the prime number P is also known by the attacker Eve. So Alice simply chooses a number between 2 to the P minus 2 and calculates G to the A mod P. And she represented with capital A and sends it to Bob. So Eve actually captures A. But capturing the capital A doesn't allow Eve to break the system, because Eve knows this capital A, she knows G, she knows P, but capturing A from here is equivalent to solving the discrete logarithm problem. So this is why we are assuming that Eve cannot capture the small a. Bob does the same thing. He chooses a random number B, calculates G to the B mod P, which is capital B, sends it to the A. Eve also captures this number. So she again knows the capital B, G, and P, but capturing small b from here is equivalent to solving the discrete logarithm problem. So we assume that this is a hard problem, so she cannot solve it. So capturing all of this information doesn't allow Eve to calculate G to the BA. So because she doesn't know small b or small a, so she cannot calculate this, but both sides can calculate this same number. And again, they might choose the rightmost, for instance, 256 bits as their secret key to communicate. So this is actually what we use in the internet most of the time. All of the secure communication starts with a Diffie-Hellman key exchange. Okay, so all this security on the internet in e-commerce or e-banking actually depends on Diffie-Hellman key exchange. So this is one example. This is about key agreement, but we can also generate encryption algorithms which rely on discrete logarithm problem. So here's an example, Al-Gamal encryption scheme. So it is very simple. Initially, you have to choose your private and public keys. It is very easy. You simply randomly choose an X, which will be your secret key. Then you compute G to the X, the group element, which is Y. And now you say that this is your public key. So it is as simple as that. Your private key is X, which you chose randomly and keep it secret. And you calculate G to the X and obtain Y. And you publicly announce that this is your public key. So whenever somebody wants to send you a message, for instance, they want to send the message M, they choose random R, because if you don't randomize the process, sending the same message will result in same ciphertext, so people can do replay attacks. So instead, for every communication, you choose a random number R, and you compute two values U and V, which are very easy to do because you know R, so you simply calculate G to the R, and also you calculate M times Y to the R. So it's simple multiplication operations. And when you want to decrypt it, so somebody sends you U and V, now what you do is you simply compute V times U to the power minus X. So let's see why this works. So U is simply G to the R. So if you take minus X power of U, actually this means that you are calculating G to the power minus XR, right? And if you multiply it with V, this is M times Y to the power R, but Y is G to the X. So R power of it is actually G to the XR. So if you multiply V and U with to the power minus X, which means that you are actually multiplying M times G to the XR times G to the minus XR. So these cancel each other, you end up with M. So as simple as that, a very basic encryption and decryption algorithm, which relies on the hardness of discrete logarithm problem, because anybody who knows your public key can try to find X, because they also know G, but solving it equals to solving the discrete logarithm problem. So as you can see, discrete logarithm problem can be used for key exchange or encryption, but again, which group you are choosing here actually determines your security. Here you can use elliptic curves, so you can use Al-Gamal encryption algorithm using elliptic curves, because this group operation depends on the group you choose. You can simply choose elliptic curve. So the question now is, should we choose an elliptic curve or not, and why actually we are not working on ZP? Actually, I said that there is a sub-exponential time algorithm, so this is why when we recommend key lengths, this is actually what you get. So in the past years, we were confident that 80-bit security was enough, but 10 or 15 years ago, we realized that now the computational power of current technology is really good, so we can break 80-bit security. So we moved on to something higher. So generally, the minimum key length we suggest is 128. Of course, NIST says that 112 bit is secure, but there's no need to, live on the edge. So we always suggest for personal use 128-bit keys, and for military use, you can choose 256 bits. So if you want to have 128-bit security, you can choose AES 128 to use in symmetric key encryption, because a brute force attack or a generic attack can break this cipher by performing 2 to the 128 encryption. So this is why we say it has 128-bit security. But due to Pollard's row algorithm, which actually reduces the complexity by a square root, this is why when you use an elliptic curve, you need to have you need to use 256-bit values, okay, due to the Pollard's row algorithm. Again, when you use regular discrete logarithm, your key length should be twice this number due to the Pollard's row algorithm. But due to the sub-exponential time attack on the discrete logarithm problem, your group size has to be 3000 bits, 3072. This also applies for RSA. Actually, this is why when we choose two primes and multiply in RSA, our modulus should be of 3000 bits. So as you can see, if you increase your security to the 256 bits, now it is enough to use 512-bit numbers when you work with elliptic curves. Okay, but now for RSA, your factoring modulus will be very huge, also in the discrete logarithm problem. So this is why most of the time we suggest elliptic curves, because we can choose smaller keys. Okay, next we are going to focus on the digital signature algorithm. So when you use the digital signature algorithm, these are the bit sizes that you need to use. But when we use elliptic curve digital signature algorithm, we will be working on this. So this was the main idea behind the discrete logarithm problem and elliptic curve discrete logarithm problem.